Welcome Calculus 3 students. We are looking at tangent planes and linear approximation today. So let's investigate this graph over here. When we first started talking about a tangent line to a particular function, we had to discuss whether or not it was differentiable at a point. And note, if we had some sort of corner cusp, we said that it wasn't differentiable at that point. We are going to extend that to the three-dimensional space, and when we talk about tangent planes, we don't always have a differentiable point. So notice this right here does not have a single plane that you could say was tangent to this point. It would be any number of different planes that would fit along this point. Over in this graph here, it shows a nice little example of a tangent plane to a particular surface, and this is what we're going to be looking at in this section. So we're given a definition. This is the equation of a tangent plane, and what it says that we're going to need to do, we're going to have something that's differentiable at that particular point, and then the gradient there can't be equal to 0, and we are going to take the partial of this with respect to x, and it will be very similar to what we did for a line. So let's see if we can follow this. I have, here's my function. I need to find the partial with respect to x, and everything else is going to be treated as a constant. So this is going to be 2x over 9. F with respect to y is going to be 2y over 25. F with respect to z is going to just be 2z. And then I am to get that gradient, so let me just write this in proper notation. So I have this gradient of f, x, y, z, and then I would write that as a vector, 2x over 9, 2y over 25, and 2z. And then I need to evaluate it at that point, and I'm going to do that. Alright, now that I have that complete, I'm just going to plug it into my formula for the equation of a tangent plane. So I need that partial with respect to x evaluated at that point, so that would be 0 times x minus the value at that point, and that is also a 0, plus the partial of y evaluated at that point, and that is 8 over 25, y minus the 4, and then plus 6 over 5, z minus the 3/5 equals 0. Now I'm just going to do my algebra and get this nice and tidy. Alright, so there's my equation for the tangent plane. Notice that this does not depend on x. They ask me now at what points on the ellipsoid is the tangent plane horizontal. Well, here's my ellipsoid, and they want to know when the tangent plane is horizontal, that would mean that both x and y are 0. So for this b part, I will plug in a 0 into my original, and I get z squared minus 1 equals 0. So this happens when z is a positive or a negative 1. So then I would say that this happens because they want to know at what point. That would be at 0, 0, 1, and at 0, 0, negative 1. And that's it for the first example. This is the same question as last time. It's just given to us in a different form. I'm given this in terms of z and instead of in terms of it has to do with being an implicit or an explicit form of the equation. So for this explicit form, I'm going to need to find the partial with respect to x and evaluate it at that point. So that partial would be minus 6x, that's it, evaluated at that point. Fx at the point 2, 1 is then going to be negative 12. Fy is, with respect to y, is minus 8y. Evaluated at that point is going to be negative 8. And then I'm just going to plug into my formula here, z equals, and that would be negative 12, x minus, what is the value of x there? It's a 2, plus negative 8, y minus 1, and then plus, and now I need to get the value of my function evaluated at that point to 1. And if I plug that into my original here and just do that computation, it's going to be 32 minus 3 times 2 squared minus 4 times 1 squared. You should get negative 12. I'm sorry, not negative 12, you should get 16, sorry. I was looking at this one. And then I'm just going to plug all of that in, so this is a plus 16, and when you do your algebra you should get minus 12x minus 8y plus 48. And there's another example in the explicit form, and the other one would then of course have been in the implicit form. In this next problem, what we're going to be doing is using that equation of the tangent plane to estimate the value of our function at a particular point. And we did this in our two-dimensional space, and we're just now before in, I guess it was Calc 2 maybe, or it might have been Calc 1. Anyway, we're going to extend that to our 3 space, and what we will be doing is once again doing our gradient. We're going to take the derivative with respect to x, leaving the y as a constant, and so let's go ahead and start this show. Fx, and it's going to be, and then I'll have to evaluate it at that particular point. So for this one I'm going to take the derivative of, it's going to be involving my quotient rule, or I could make it say could do it with the chain rule. Let's do it with the chain rule. Let's go ahead and make this read 5 times x squared plus y squared to the minus 1. I like it this way. Alright, so I'm going to take the derivative of the outside, leave the inside alone, minus 5 x squared plus y squared, and then subtracting 1, that would be a minus 2 times the derivative of the inside, so that would just be a 2x. The y is treated as a constant. So this would then give me minus 10x over this x squared plus y squared, quantity squared. I'm going to do the same thing for y and evaluate my points. Alright, I went ahead and got all of those numbers crunched, and now I'm just going to plug into my linear approximation formula. So I'm going to say the linear approximation of whatever point that's going to be near there, and it does have to be near there. It's going to be 2/5 x minus the negative 1, so that would be plus 1, plus fy minus 4/5 y minus 2, and then plus the 1. I'm going to do my algebra here, and I'll get back with you. Alright, there's what I get for my linear approximation. So I'm now going to do the linear approximation at negative 1.05 comma 2.1, and I'm just going to plug in those values for x and y and crunch it. Alright, there's what we get. Now if you were to actually plug it into the exact function itself, you'd get about 0.9, which is pretty darn close. We're going to change this up. Now we're going to do an approximation using a differential, and we're going to find what this differential is for z. How does this change as it goes from one point to the next? This is the same exact problem from example 3, so I'm just using that data. Now I've got to get what dx is. Now I go from -1 to -0.93, and that is an increase of 0.07, so that's positive. dy goes from 2 to 1.94. Now that's a decrease, so I will let dx be a -0.06, and I'm just going to plug that in and crunch those numbers and come up with the differential dz. Alright, and this is what we get. If we were to compute that actual change from one point to the next for our z, that would actually be about 0.080, so it is once again pretty darn close. My next problem is a word problem or an application problem where I'm going to use differentials to approximate some sort of realistic change in BMI when weight increases. So they're asking me to use differentials to do this, so what I'm going to need to do first up is get the differential and evaluate it at each of those 2 points. I'm going to get the differential with respect to W and H and evaluate it at those points. Alright, so what I've done is I've gone ahead and gotten those partials, and the B is going to equal to, I'm going to evaluate at that point, so W is the first one, H is the next one, so this is going to be 1 over 1.65 quantity squared. How does my H change? My H goes from the 55 to the 56.15, so that's an increase of 1.5, so this will be multiplied by 1.5, and I'm going to finish this up for you. Alright, and there we have our differential. We have how the BMI changes as a result of a change in both weight and height. And I believe we did an increase in weight and an increase in height, just to see what's going on with this change in differential. Our next problem wants us to look at this in terms of a relative change instead of an absolute change. So we're going to change this formula somewhat so that I can get relative change introduced to this. The first thing I need to do is divide our differential equation through by the BMI in order to get this relative change. And now I'm going to plug in our values for my BMI, or plug in my equation actually. Alright, now with this being my relative change in W and this being my relative change in H, well, I guess it'd be the whole thing, I'm now going to say a 1% change results in a 1% change in my weight results in just a 1% change in the body mass index, but notice that a 1% change in height results in a 2% change in the BMI, so that lets us know that the BMI is more sensitive to a change in height than in weight. In this problem they're wanting me to compute how the differential in volume relates to a change in any one of these different parameters, radius, height, and time. So I'm going to need to find my all of my different partials with respect to radius, height, and time and plug in at the particular point. So my point being, I believe, the point 10, 50, 0.1. So I'm going to take those partials and then get the values for my partials. Alright, here is my pertinent information. This is just like the last one, just but they just gave me some values, and they gave me tolerances here and here, and so I needed to find my differentials and my gradient, and now I'm getting ready to just plug this in and crunch out an answer. Alright, so here we have the differential and how that volume changes as a result of these different changes in the different parameters of this cylindrical tube. And if you have any questions, be sure and see me at the Collaborate or email me. Alright, have a great day.